So the equivalent model of a certain op amp is shown here. Determine the input resistance, the output resistance, the voltage gain in decibels. Okay, we don't have to do it in decibels because that's not how it's ever performed, like shown to us. But I guess that's the input resistance. That's the output resistance. That and the voltage gain in decibels. Well, that's A. So well, it doesn't matter. Like there is some way to convert it to decibels, but I just control F. I saw it in here. Somewhere here. There we go. Voltage gain is expressed in decibels. So A decibels is 20 log base 10 of A. So 20 log base 10 of 10 to the 4. Sorry, 20. So that's just going to be 80. 80 decibels. Great. That's that question then. 5.5. So 5.5.
Was it only C that we had to answer?
We did all of them. Input resistance was that.
Oh, so you're just labeling. Okay, okay.
Just labeling.
Yeah.
5.5.
Wait, is that the right answer? Or is it?
It must be.
I mean,
there's
yeah.
no other way.
Yeah. Do you want to put someone gets later, maybe?
Oh yeah, I'd like to check some.
They changed later, but I have them like the new version, Quizlet.
Okay. Yeah. Yeah. Great. If you have anything.
Yeah.
What was it? 1?
Yeah. 5.1.
So what was your thing? 80?
80 decibels.
They got 98.06.
Oh yeah, because I did a stupid thing. It's 8. It's 8 times 10 to the 4, not just 10 to the 4, is it?
Yeah,
so,
it's 8.
Then I'm gonna just plug that into my calculator. That I get 20 times log base 10 of 8 times 10 to the 4. 90. I got 98.1. Is that what they got?
They got. Yeah, you rounded it, right? Okay, yeah.
98.1? Yeah, okay, good. There you go.
Yeah.
Yeah, of course. I just forgot the 8. How did I do? I don't know why. I'm making stupid mistakes. Okay, 5.5. For the op amp circuit in this figure, the op amp has an open loop gain of 100,000. An input resistance of 10 kilo ohms and an output resistance of 100 kilo ohms. Find the voltage gain V naught over VI using the non-ideal op amp model. Non-ideal model of the op amp. Okay. Have we ever really dealt with non-ideal model of an op amp? Yeah. Well,
Yeah.
we have.
We did, yeah.
Okay, so I'm just gonna convert that. So this will be a ground. And this will be some input there, and then it has that resistor there, and then there, and here we have, yeah, here we're also connected to ground, and it's a dependent voltage source, and then it leaves like this resistor there, that, and then that. I guess I should. Where should this come from? That should come from there, I guess. Doesn't really matter. It's all ground. So, okay. So we have that. Now this is A, and then this is V. This is V1. Which is the positive one? So then this is V1. This is V2. So this is A V1 minus V2. I think that's right. Let me check if that's right. I don't want to have them just it in reverse order. So yeah, the minus is the minus of the voltage. Yeah, okay, there you go. So then that would be plus minus. Yeah, okay, so it's V1 minus V2. Yeah, okay, that looks right to me. So this is our I and this is our O. And what are we looking for? We're looking for VO over VI. Just to avoid that a little bit. That can just connect there. So VI is that. So V1 equals VI. So I guess what we can do, is this built right? I think it is built right. So we do KCL, KVL, process loop. Yeah, I think we do KCL across. No, KB. Yeah. Okay. That seems right to me, I think. So doing that, I'd get negative VI. Yeah, negative VI plus VI. The voltage is I times R. So there's an I there. The voltage across the resistor is I over R. No, I times R. But we don't know the current. No, the voltage across the resistor is V1 minus V2. Yeah, I think. Okay, whatever. And then here, that's plus V2. No, I'm doing this wrong, aren't I? That's not right. How do we do this again? Look at my notes, I guess. Did it in the lecture. For the non-ideal ones. Because for the ideal ones, of course, we can just make those assumptions. But for the non-ideal ones, I want to see. Ideal. I don't want to see the ideal one. I actually have very little written for the non-ideal one. I literally have one example. Oh yeah, because never mind. I know why I only have very little written. Okay. Yeah. Okay. So he does do KVL. He does do KVL across the loop, and solve a question like this. And so he gets. So just call this VD here. VD plus minus. So you're going to get negative VI plus VD. Fine. And then the voltage across here he just calls Vx. He does it. Oh no, but why would you even need to do that? Wasn't even used. Where's VO? Oh, and then you know the voltage from here to here. Yeah, okay. So you know the voltage from here to here. So essentially you're doing... Okay. So then plus VO equals 0. Yeah, there you go. So he does that. And then you can find that this... So you're finding VI... VI over VO. V over V. I mean, VD is V1 minus V2. How does he do it? I'm just looking at an example here. Let's just like take a look at an example he does and then see if we can apply it. So he does this circuit, whatever, some resistance there. Very similar circuit. This is VI. And then he does that, and then he does that, and then he does that, that, and these are both connected to some ground. Okay. So this is VO. This is VD, that's VI. So then he does KVL, he gets VI minus VD minus VO equals 0. So he's doing it essentially that way, kind of, right? And then from here, that turns into VD equals VI plus VO. That doesn't make sense. V minus. Yeah.
Is the dependent voltage source included in the KVL?
Essentially, what you're doing is you're just taking the that the voltage difference across this whole thing is VO,
Oh, okay. Oh,
right?
okay. So yeah.
Right, so you just I mean, I guess that's what these do. That's weird. That rearranges to VI minus VD minus VO. I must have just copied it wrong, I guess, because that doesn't rearrange to that. That over VI minus VO. It should be a minus, I think. And then he gets here VO equals the specific thing here was 100,000 VD. 100,000 VD. So VO. Oh, and then it's just the addition of these two. Yeah, okay. So this is plus minus VX. So VO is 100,000 VD plus VX, right? The resistance across the voltage across that. So combining these equations, we get VD equals VI minus 100,000 VD plus VX. Okay. But VX is negligible, apparently. According to the example here, VX is negligible because
Is that because it's non-ideal?
no, yeah, well, no, because ideally it would be completely zero, but since it's not ideal, it's just negligible because this is a 10 kilo ohm resistor and that's just a 100 ohm resistor. So since it's negligible, you can just turn this equation into VD equals VI minus 100,000.
So whether it was ideal or non-ideal, you're still gonna ignore the VX.
I guess so. Yeah.
Okay.
I'm just following this example. And then we were looking for VO over VI. So okay, here, so that X goes away because it's negligible here. So VO where did VD disappear to? VO equals 100,000. Wow, okay, sorry. Did I make a mess of this? No, I didn't make a mess of this. I think it's just weird. VD minus VI is what we have here. VO is 100,000 VD plus VX, but VX is negligible. So that gives us VO equals 100,000 VD. Okay. The next thing I have.
I think you.
Yeah.
Sorry, I think you plug in VD instead of VO. Right.
Plug. Oh, rearrange this for VD and then plug it into here.
Yeah. So see how it's like already
okay.
rearranged for VD, right? So you just plug it in and then. I think. I don't know.
Yeah. Plug VD into here.
Yeah.
Oh, okay. So VO equals 100,000 VI minus VO. Yeah, that's what you do. Yeah. VO, and I'll just, well, we're looking for VO over VI. So VO equals 100,000 VI minus 100,000 VO. Do whatever. So we get VO equals VO over VI equals, it'll be 100,000 over, well, so 100,001. Yeah, it's approximately 1. Yeah, there we go. Okay. So I guess that was the answer. We did get 1 there. Yeah, we did get 1 there. That's fine. Okay, so now let's try to apply that to this. Let's try to apply how he did this. So with this one, if I go my PCO, yeah.
Yeah, so it would be VD equals VI plus but we're not given the dependent we're not given the A value, are we?
We are, yeah. I just didn't write it. We're given A We're given
Oh,
both resistances.
yeah, okay. So then, yeah, we could use that same equation that we had down there.
Yeah, so it'll be minus VI plus VD plus VO equals 0. And then I want to note that VO equals A VD plus VX.
Yeah.
Right? Substitute, well, no, rearrange this for VD. So VD equals VI minus VO. Substitute that into here. OneNote is freaking out on me sometimes. Try that again. It's the bottom. There we go. Okay. There. Okay. So now substitute that into here. VO equals A VI minus VO plus VX, but VX is, I guess, negligible. So we can just take that away.
Are we asked to find the ratio of VI over VO?
Yeah.
Or VO over
VO,
VI?
yeah.
Okay. So that's why we're subbing in VI minus VO for VD, right?
VI minus VO for VD. Yeah, because we want to. Yeah,
Okay.
because we want to get rid
Exactly.
of VD.
Okay, makes sense.
It's AVO, and we're doing. So it's going to be VO over VI is going to be A over 1 plus A, which is approximately 1. In fact, that's even in my notes. That's even in my notes. I even go through it here. Actually, the exact question. I guess, yeah. So you have that, and then, yeah, you can get the. I guess, yeah. We can solve for this essentially is all the steps, and then we're essentially taking the limit as a goes to infinity, right? We're looking for infinite amplification, so you'll have a output of 1 for that. Like, I mean, sorry, an amplification factor.
Yeah.
Ratio of 1. Yeah. Okay, there we go. We figured that out. At least that got that. Let's move on. 5.7. Of course, anybody stop me?
Yeah, can you go to that last
Yeah.
line? No, right above.
Oh, yeah.
Because yeah. So over here, so when you're isolating to get VO over VI, how exactly? So I know that you can move the VO over to the other side, and then you could
Yeah.
factor it out.
Yeah.
So now VO equals 1 plus A, right?
Yeah. Well, VO times 1 plus A equals A VI.
So then you could factor out VI from A, I guess.
Well, it's already factored. It's pretty much. So you just want to divide both sides by 1 plus A, and then, but also by VI. Right? Because, and you get VO over VI equals A over 1 plus A. You get exactly the next line.
Okay, that makes sense.
You see how I did it?
Yeah, it's almost like a cross multiplying sort of thing.
Yeah, it is. It's exactly. Okay, 5.7 is next. Yeah, 5.7.
Sorry, I just have like one
Yeah.
quick one. Yeah. So that negative that first equation you got, that negative VI plus VD plus VO equals to 0. That's through KCL?
This one?
Or KVL?
KVL.
Yeah, that one.
KVL. Yeah.
KVL.
I know. I always
Okay.
say the wrong one too. But yeah.
Okay. Yeah.
KVL. Yeah.
All right. Okay.
Okay, let's look at 7. So 7 is this guy. The op amp in this figure has an input resistance of that, an output resistance of that, and an amplification of that. Find the differential voltage VD and the output voltage VO. Okay. Okay, I guess I have to draw this with the, I have to turn this into like the non-ideal with the resistors and everything, so I'll do that first, I guess. So plus minus, this is 1 millivolt. Then we have a 10 kilo ohm resistor. And then we have a Yeah, I'm gonna have to draw it like this. Okay, so then there's some resistor, I forget what it is. This connects to ground. Don't want to do it so messy, so I'll just draw a ground here. And then we have here coming also from the ground another thing like that, which outputs like that, and then it has its whole AVD here. And then there's a resistor here. I bet you guys didn't miss my drawings, did you?
Looks fine.
And then this connects like that. This is a ground. This VD is here. So plus VO minus, by VD I mean VO, obviously. There, okay. There's the circuit with that. Of course, these resistors have values, but that's a 10 kilo ohm resistor, and then that's a 100 ohm, and that's a 100 kilo ohm. Okay, so we are tasked with finding the voltage. I think it's plus minus like that. No, plus minus like that. We're tasked with finding VD and VO. Okay. Can't we do this? Can't we do this just by? Well, it's hard to tell. It's such a messy circuit that I can't even really tell what I'm looking at. The voltage here. Since we're trying to find so many node voltages, can I just do nodal analysis on that node, that node, that node, that node? I think I can. Yeah, I think I can. Whoops, I can click that. So this is V1, V2. Let's just give it a try. If anyone has any believes I can't do this for some reason, tell me. V1 equals 1 millivolt. So I'll say, yeah, whatever, 1 millivolt. Great. Now, next equation is the V2 equation. So assume everything's leaving. So we have negative no, the voltage is, yeah, so V2, so the current leaving, I is V over R. So V2 minus 0 over 100 kilo ohms. So, what did you say, sorry?
Yeah, and then plus V2 minus VI, which we know, over 10 kilo ohms.
V1, yeah, V1 over 10 kilo ohms, yeah. And then we have
V2 minus V4.
Yeah, good. Okay, that's that equation. And then we have, yeah, that's fine. Is that fine? Killa and the Killa.
I don't know, just because of the fact that isn't there like specific rules where it's like you can't do nodal analysis, or you have to do nodal analysis a certain way when you have a dependent voltage source or something like that?
I forget about the dependent, yeah. I forget anything about the dependent voltage source being there. I can look at my notes. I read it over
The
today.
dependent becomes the node voltage. So V3's voltage would be the same thing as a dependent.
Yeah, just AVD.
Yep.
And the voltage there is, just VD is equal to negative V2.
I'm not sure about that part.
Yeah, I think that is right what it says. Okay, yeah, okay. So we'll try there. I guess I'll say that now. V3 equals AVD. Great. And then we have V4 is V4 minus V3 over 100. Minus V3 over 100 ohms. Or, I'll just do everything in kilo ohms, so 0.1 kilo ohms. Then I have V4 minus V2 over 100. V4 minus V2 over 100 kilo ohms. And that is fine now. Okay, equals 0. Now I want to say VD is equal to 0 minus V2. Okay, 0 minus V2. Okay, good. So I just need to solve for V2, and I get VD, which is good. So I can actually put that in right here. Yeah, that's actually good.
Yes, sir. Can you go back up?
Yeah.
VD is equal to 0 minus V2.
Yeah. 0 minus V2.
Yeah, okay. Yeah, we're good.
Okay, so there, I have that then. So then this can equal A, well, so obviously, but A times that. There you go. 0 minus V2, so negative A V2, that's V3. And I know what A is, so that's fine. Okay, so now I have my system. I have 1, 2, 3, 4 equations, 4 unknowns. Okay, we're good. The millivolts and the kiloohms are going to screw me up, aren't they? Should I just turn everything into just volts and ohms? I feel like there's a way to not do that, but 0.001 volts. So we know that. V2 over 100,000 ohms plus V2 over 10,000 ohms minus V1 over 10,000 ohms plus V2 over 100,000 ohms minus V4 over 100,000 ohms equals 0. Same thing here, V3 equals negative. A was 100,000, yeah. 100,000 V2, V4, that was 100 ohms, so V4 over 100 ohms minus V3 over 100 ohms plus V4 over 100,000 minus V2 over 100,000 equals 0. Okay, somewhat of an improvement in our system. Yeah, that's good. Okay, now I can simplify, obviously. Just seeing if there's any smarter way I can do this. Okay, I'll eliminate one of the unknowns. So obviously we know V1 is 0.001. Okay, so now V2, this is going to be 2 V2 over 100,000, which is going to be V2 over 50,000. Minus V1, well, V1 we know, so 0.00, well, what's 0.001 over 10,000? I know I can do that with some powers of 10, but whatever. 3. So I get, I just get a constant 1 times 10 to the negative 7 plus V, oh, there's another V2 over 100. Oh, yeah, never mind. I made a mistake, and then the mistake canceled that, so V2 over 10,000, so then I can just combine that there. V2 over 10,000 minus 1 times 10 to the 7 to the negative 7 minus V4 1,000 there, so 1 times 10 7. Great. V3 equals that whole thing, so I'll leave that as an equation. So 100,000 V2 plus V3 equals 0. And then here, this stuff can add. So this is going to be V4 over 100 plus V3 over 100. So I can add this stuff. So what's, I'm just going to use my calculator. 1 over 100 plus 1 over 100,000 is apparently not a fraction. But anyways, 0.01001 V4 minus 1 over 100 V3 minus 1 over 100,000 V2 equals 0. Okay. 3 equations, 3 unknowns. How do I find VO after? VO is the whole big voltage difference. No, it's just V4. Never mind. VO is equal to V4. Okay, great. So now I know how to find all the voltages. Anyways, so let's do the, oh no, I have to add that still. So 1 over 50,000 plus 1 over 10,000 is 3 over 25,000. So this is just going to be 3 over 25,000 V2. V2. Yeah. Okay. RF calculator time, I guess. Look. It will be a 3 by 4 matrix. And the coefficients are V2 first, so 3 over 25,000. Nothing for V3, so 0, negative 1 over 100,000. Yep, and then 0.1234561. Great. Next line. 100. That's supposed to be one positive. Yeah, yeah. 100. And now for V2, I have negative 1 over 100,000, negative 1 over 100, 0.01001, 0. Let's see if we get anything, any kind of value. Does anybody have the answers for this one?
I do.
Slater? Yeah, you do?
Okay, yeah.
So this is what I get out of my RREF. So we said VO was V4. That's the last one. So is the answer negative 0.001 or negative 1 millivolt?
Hold on. So
For VO. VD.
wait, could you like scroll up to the question? Sorry.
Yeah. Here?
Yeah. Okay. I have it pulled up on check. Sorry, he didn't sound
No worries.
later. Oh.
Yeah.
Okay, wait, maybe check that doesn't have it.
No, it doesn't have this one?
Here, let me check this one here. The Quizlet thing, right? Oh wait, I don't have the membership. Rip. Someone else check.
Yeah. Does anybody else have it for 5.7?
Yo, sorry to interrupt.
Yeah.
You're gonna be posting this on YouTube, right?
Well, I just posted unlisted. So, but yeah,
All right.
these ones I just posted unlisted.
Yeah, I'm gonna tune in later then.
Yeah.
Gotta
yeah.
go for now.
Sounds good.
Easy,
sounds
guys.
Good. Have a good night. See ya.
You too.
Okay, so does anybody else have the something solutions for something?
Yeah, I don't. Honestly, I
don't?
don't.
And Slater doesn't have it?
Checking. Okay, so chapter 5, right?
Yeah, chapter 5.7.
0.7. Yeah, it's just yeah, it asks for like a free. It asks for a trial here.
Oh, maybe because I didn't do it recently. Maybe it'll. Like, did you look up answers recently, and that's why it's not letting you?
Yeah.
Do it. Okay, so let me see. Slater fundamental electric circuits. This is. Do you know what edition we have of the textbook?
It's 6th.
6th. Okay, no, just check it. So actually, I have 7th. So I'll go with that. Quizlet. What? What? That's weird. I'm clicking. What? Wow, really weird thing was that. Oh. Slater just forwards me to Quizlet for some reason. Everything's forwarded to Quizlet.
Yeah.
Oh, is it owned? Did they like buy it or something?
Yeah,
Oh.
I have Quizlet Plus if you want though.
Yeah, what do you have access to the answer?
This is 5.7, right?
0.7, yeah.
I do, yes. You want me to share my screen?
Sure, I guess. Yeah. Okay, is that the same thing that we have? 1 millivolt, 10 kilo ohm, and then negative. And then where's the positive B? Negative VD, AVD. And that's just connected to ground. There should be another ground there. Oh yeah, just the positive. Oh, they just drew it upside down. Good. Okay, it is nicer. They draw it like that. Okay, yeah. Yeah. Okay, so VD Yeah, keep going. Let's just see.
You want to just give you the final answer?
Yeah, I guess so. So VD. Oh yeah, you got VD was that. What'd you get for VO? VO was -1 millivolt. Yeah, -1 millivolt. Oh, -10 millivolts. So I got. Did I get the same thing? 1, 2, 3. Yeah, no, I got the same thing. I just wrote it wrong. Yeah. I just wrote it. Never mind. Yeah, we got VO right, and then VD. I just wrote this wrong. It's supposed to be a 1 there. And then that's -10 millivolts, which is approximately what you got. And then VD is. How do I get VD? V3 equals AVD. Oh, no. But then we determined that VD was equal to -V2. Yeah, and then V2 I got was that, so VD is 0.01 volts. So that's going to be, oh, is that what that's not what I got now. Interesting. 0.01 volts. That would be, yeah, not the same thing. Not the same thing as your answer there. Okay. Interesting that we didn't get VD. VD is 0 minus V2. Yeah. 0 minus V2. Yeah. So I should just have negative V2. Oh no, V2 is this one. There we go. That's what I'm drawing. That's wrong. That's V3. That's V2. I was just looking at it wrong. There we go. So 0.00. Wow. Okay. 0.1 times 10 to the -1, 2, 3, 4, 5, 6, -7. Okay, and I think that's what the answer was. Approximately. I don't know. I can't remember now. It was negative. Yeah, that is what it was approximately. So there you go. Okay, so we did get the answer.
Yeah.
Do you think you could just go over the whole process again?
Yeah,
Because I kind of got lost on the way.
Essentially,
My
whenever
internet died in the middle.
yeah, I did it. Oh, okay. Well, we got the right answer, so that's good. So we start with this. It's a non-ideal op amp, right? So you have to turn it into the resistor stuff and all this whole complicated thing.
I see.
Right?
Okay.
So we turn it into this, and then I did nodal to figure out what our goal was: VD and VO. Right?
Yeah.
So VO is V4, VD is -V2, and then I just did nodal, but the nodal took a while, and I figured it out from there.
See. So could you scroll back up? Okay. A bit higher, just where you started like assigning the nodes. So yeah, right over here, V3. So what Awais pointed out was that V3 would be whatever the dependent source that's right next to the node. So V3 would be AVD, and that's always the case.
Yeah, I said V3 was it.
Yeah.
And then I noted that VD was 0 minus V2, and substituted that in.
So that means VD would equal -V2, right?
Yeah, exactly.
I see. So why wouldn't it be V2 minus 0?
Because you do the positive
It's
terminal minus
positive,
the
yeah.
minus terminal. And it's
Okay,
positive
and that
because
was
the zeros.
indicated. Yeah, okay, good. All right. Yeah, that makes sense now. We're good.
Okay, good. Okay, there's that one done. Let's take a look at 5.9. There's 5. Okay, so now we're in ideal op amps, which is good. Determine VO for each of the op amp circuits in this 5.48. Yeah. So we can just treat them like ideal op amps. So VO is our goal. So when we say we want to find VO, first of all, we know that 0 amps is going in here.
Also, unless specified, we assume that it's ideal.
Yeah. Unless they give us what RI and RO is. They tell us what those resistances are, then it's fine. And then we can just say that this is the same node. This is all one node. Okay, since it's ideal, because since there's 0 amps going in here, the voltage difference is 0. So that whole thing is 4 volts. So 0. How do we do this again? I need the voltage there essentially.
I think you need to do nodal analysis at that node.
At that node right there. Is that how I do it? Let me try to just remember quickly.
I think so.
Oh yeah, what I think I remember we do is yeah, this volt. Yeah, because this current is yeah. Okay. So this current is entering. There's 0 amps going this way and some current going this way. I'll call that I. Right? So we know that I is equal to 1 milliamp. Right? But because there's no other way for it to go. It has to go there. But we also know that I is equal to 4 volts minus VO. So I'm quite certain that we can. That doesn't make sense.
That makes no sense. How?
Over 2 kiloohms. That now it makes sense.
Yeah. Yeah.
There we go. And I'll just say 2,000 ohms. Now I can say 4 minus VO over 2,000 equals 0.001. And we can just solve for what we want. So 4 minus VO equals 2. And 2. VO equals 2.
Yeah, that's what I got.
And is that right?
I'm pretty sure. Here, let me check.
Yeah.
Check. What was this? 9.
9.
Wait, quick question.
Uh-huh.
In that 4 minus VO expression that you have there, why is it 4 minus VO? 4V
Here?
minus VO.
Here, this right
Yeah.
here. Because it's just your like what you do with nodal, right? When the current's going this way, it's the voltage here minus the voltage here. So the voltage here is 4 volts because this whole node has 4 volts because of that voltage source.
So we're just assuming that that entire node on the left is 4 volts.
Well, because it is with an ideal op amp, it is 4 volts.
Well,
Yeah, what he circled in blue is the whole node.
Yeah.
So if that voltage
Including
source
here.
is right there, yeah.
Yeah, it's 2 volts. Yeah.
2 volts? Yeah, okay, good.
VO is 2 volts.
Okay, let's give this one a try. So it'll be a similar thing, I'm quite certain. I think we just say, let's see, okay, interesting. So okay, so this is negative feedback still. I'm sure this is the same thing, but it's just confusing to look at. So VO is there for some reason. Okay, so it's not the same thing really, because that's VO. Here we do have negative feedback. If I just flip it upside down, let's see if that helps us at all. To be more with how we're used to seeing it. So if I make that the plus and that the minus, that has a source like that coming at it. So this is usually how it's drawn, with the negative like that. And then there, and then here I have a 2 kilo ohm connected to. Okay, so that's interesting because the voltage out here is the voltage difference. So there's no amps going in. No amps going in. Because that resistance is infinity. That's weird. Because
Okay,
that
so
would mean
what
that
I'm
this
thinking,
is 1, this is 3. Yeah.
so if you follow that 1 voltage source, that 1 volt voltage source, it leads to that node at the end, right? As the output node.
Yeah,
No, if
there.
it goes the other way. So that means at that node right there, that's negative 1 volt, right? At that node, at the end as the output.
Not necessarily. It just means that this minus this is 1. That's all we know. Is that the voltage here, whatever this
So,
voltage is?
Because, okay, you know how for voltage sources, whatever's on the, yeah, that node. Because, like, for example, we made that assumption for the previous example, right? Where the node right above it, like, yeah, exactly that. That would be 1 volt.
It would be 1 volt higher than this. In the last assumption, in the last, well, yeah.
Oh, yeah, so.
Here,
Okay, I see.
we could say, you know this is 0, right? You know this is 0 volts, right?
Mhm.
So that's why we can say 0 minus V2. We can actually put a number to it here. But here, we just know the difference between the two nodes, that this is 1 volt higher than this.
Mm-hmm.
So I can't just assign this like a voltage of 1 volt, because we don't know that. In fact, I particularly don't know that because if that would mean this is the ground. If this was 1 volt, because this is 1 volt higher than that. So that would imply this is 0.
So if there's 0 amps, that means there's 0 volts, right? That's not, or is that not always the case?
0 amps. That means there is 0 voltage difference across these pins. But that's obviously not. Oh no, is that obviously not true? Oh no. There has to be a 0 voltage difference across these pins. I know the voltage here is 3. The reason I know that's because that's ground. So compared to ground, that's 3 volts. That means that this must also be 3 volts. Just because an ideal op-amp has to have the same voltage across the 2 pins.
Oh, so that means the node, in green is 2. Yeah. And there you go, that's VO. Yeah.
Is that also the answer? Ronak, if you have it, or if anyone else.
Oh, sorry.
Don't worry. For
5.9B.
Oh, for B. Okay, so I got 2.
Yeah.
Is that what you got? Yeah,
I got 2. Yeah.
Okay, yeah.
Is that the answer?
I'm pretty. Yeah. Yes, 2. Yeah.
Okay, good. Great. That was a good question. I like that because it forced us to actually think about that. We know that these voltage difference should be 0. I'm gonna write down that question. I like that question.
So could you also go the other way around and assume that the node that you colored in purple is 1 volt because of that voltage source?
No, we can't say that. We just know that this minus this is 1 volt. We know that this minus this is 3 volts.
Oh, it has to be 3 volts because there's the ground.
Because there's a ground. If there was a ground here, totally, we can say this is 1 volt.
Yeah. Okay.
But there's
that's
no
cool.
ground there.
Mm-hmm.
Yeah.
Oh, okay, that's why. Okay, yeah, that makes a lot more sense. I thought it was like 1 volt first. Okay.
Yeah.
So what you did here was just 3 minus 1, and then that's your VD, and then whatever output comes out of that. Okay, yeah.
Yeah, and then and then this is ground. This VO is connected to ground on this side, so it's just whatever voltage is there, which was 2 volts.
Oh, okay, yeah, that makes sense. Yeah, that's a good way of thinking about it. Yeah.
Yeah. Good. 5.11. Let's give that a try. 5.11 is here. Design a problem. Okay, I think we can skip that.
Yeah, we can. Yeah, you can skip that. I didn't want to do it.
Let's just. We're not in teachers' college. That's okay.
Didn't they tell us to design a question on the midterm last time?
They did.
I was about to say that. Yeah.
Oh my god.
Okay, let's give this a try. Go.
I was tripped. Oh wait, I don't think it was this one. Never mind.
No,
okay.
never mind. Okay, so this one is let's see. We have to find VO and V and IO. Okay.
Let's do nodal, right? I feel like that would be ideal in this situation.
So first of all, 0 amps. This is it's a negative feed. First of all, I should have confirmed negative feedback. Yes, we have negative feedback. Okay, now that I've confirmed that.
Why do you have to point that out exactly?
That's the only time we can make these ideal assumptions. That this is all the same voltage here. This whole node like that. Actually, it's.
And also for the negative feedback, it has to be coming through the negative terminal, right?
It has to go through the negative terminal.
Okay.
So that's all one node there. And so now that I know that, I think I can make.
Wait, so how do you confirm it's like negative feedback, right?
That there's a wire coming from the output, to the negative terminal.
Oh, okay. Yeah, okay.
So let me just specify that. Right there is 1 like that. Okay.
We'll just
Now-
call that one V1, right?
Sure. Yeah. Whatever.
Yeah.
Yeah, that's fine. Then I have a node there. Whoops. I have a node there. Wow, what's going on? Pen doesn't want to let go. Okay, there we go. And then I have a node there, and that's it. Actually, only have 3 nodes.
Okay.
So I don't quite know. Oh yeah, I could just say okay. I think this might work. So V1, V2, V3. So V1 equals 1.
Mm-hmm.
Great. Now, V2 equation is going to be, well, V2 minus 0 over 90. So 90. Okay. Plus V2 minus V1 over 10k. Great.
Yep.
There's no amps going that way, so then I just have to compare here.
V2, yeah, minus 0.
Minus 0 over 50k. V2 minus V3 over all over 100k. Okay, there's that equation equals 0. And then the V3 equation is negative I naught plus V naught over 10k, but that's really, no, I shouldn't say that. V3 over 10k.
Yep.
And then plus V3
Minus V2.
minus V2 over 100k.
And then also you could just sub in the 1 for V1 for your second equation.
Yeah, that's fine.
So 2 variables.
Uh,
Yeah, then what are we going to do about that negative
yeah,
I naught?
That is troublesome.
How do you have V2 over 10k twice? Shouldn't it just be the V2 minus 1 over 10k? What's the first one doing there?
This one, that's a 90k.
Yeah. Oh,
That's from that.
yeah, I was wondering.
Yeah, that's just my writing. Okay, yeah, we do have an issue with that I naught. Okay, so output there is that. Okay, this makes me think. This kind of makes me think I should do mesh. But then do I no? But then do I include a mesh here? I don't think I include a mesh there. VO and VI. We just on V3, that'd be fine.
Could we also like what if we start thinking inside the amplifier? You know how like you kind of did that thing where
the thing is that we don't know any of those resistor values. They don't give us those resistors inside. So I think we just assume it's ideal.
Yeah, you assume it's ideal for sure.
So does that if it's an ideal situation, does that suggest anything for the current output?
I don't know.
Or no?
Let's take a look at maybe. Let's take a
Oh
look.
wait. For ideal, right? Don't you like assume that Ri is like infinity and then the other one's zero?
Yeah, so you do assume that, but so then drawing that wouldn't really help us. But you're right, that is what we assume. And that's kind of why we have this 0 amps, and that's why this is all one node.
Oh, okay.
That's what causes there. Equals. There's no voltage drop, so I is R. Okay. I'm kind of thinking that we need to break I naught into these two currents because it's equal to those two added together, right?
Okay.
But obviously that's just this equation. That's just this one. Like what I just said there.
Yeah.
I naught is equal to those two currents is exactly what our last equation is here. So that doesn't really help us because I define what I3 is. So
could we find a solution on something?
Yeah, anybody got a solution for this one?
Oh wait, so So wait, for V3, is V3 equal to VO? Where is that?
V3 is equal to VO, yeah, because there's a ground on the other side.
Oh, okay, alright. I can try finding it. Was this 13?
This is 13, yeah.
Okay. Here, let me just share my screen. It's a weird thing. Okay, yeah, so this is the diagram.
Okay,
Did it?
see? Okay, I see now. Yeah. Wait, hold on. Actually, I don't see. Loading.
Yeah, it's loading for me.
Okay, wait here. Let me just reshare it then.
Yeah.
How about now?
Still just loading.
Still loading.
Okay, wait here. Alright, here, let me just.
You want to just send a screenshot?
Yeah. Okay. Here, stop sharing. Okay. That's 1.
Okay, that's okay. So we get, yeah, we get. What? How do they only get that? What? V1? They get V2 minus 1 over 10 plus V1
Hello?
over 90.
Hi.
Hey.
Hello.
Yo, what question are you on?
5.13.
Oh, okay. Wait, are you doing the ones that are assigned?
Yeah, doing the ones that are assigned.
Alright.
The list up here. Okay. No luck with this one. Like,
So they did a KCL
but how did
around.
they get a different KCL, right? Yeah, they did.
So where does the KCL loop go around?
Oh, maybe when they did KCL, they treated these as different nodes. Call that maybe V4, and then just at the end include an equation V2 equals V4.
Okay, but how would that go about finding VI though? Because I don't see VI in any of the solution.
Yeah,
That's V1, I think. Is that not? Or is that VI?
Could I see their diagram? Is there a diagram on it too?
Oh, yeah.
Just want to see what they labeled what.
Wait, which one's the actual answer? 2.7?
2.7. Yeah, we're looking for two numbers. We're looking for that voltage and that current. So the voltage is 2.7 and the current is that.
Wait, I think I tried this question. I think I got it right. It's the same answers that are
Yeah.
here.
Yeah, so let me just see how they did. Okay, so they did V1, V2. So they did label those different nodes, but they did say what I said here. They said at the end V1 equals V2.
Yeah.
So they're both 0.9 volts. Oh, they split it up into V2. Okay. What? How did they solve?
Wait, can I see your solution? Maybe I can help.
Yes, please.
Oh, I see what they did. So they only did KCL at this node. Yeah, that actually makes sense. Okay, that makes sense. Because then you can find direct. Okay, so this, they found this current and this current. Since we know there's no current going this way, 0 amps, right? That means essentially that the current going this way must be equal to the current going this way, right? That's essentially what we learned from that, right? Or in other words, these two currents are.
Oh, so then you follow it, and then you find the current going through the 50 ohm and the 10.
Yeah, so that would be V1 minus 1 over 10K plus V1 minus V1 over 90K equals 0. And you can just solve for V1 there. and then you just not mention, but you also just like note after that v1 equals v2. So we're just gonna assume you can solve this for v1 equals 0.9.
And then that's equal to v2, and then you just do another nodal analysis at v2, right?
Yeah, let's take a look. So then essentially you can ignore this section. You can ignore everything on that side after this, because you figured out this voltage here. So now you know this voltage there, and so from there we can just look at, maybe we can just look at this, just that as our circuit. No, but there's no voltage source there, so that doesn't make sense. So we can't just look at it. Okay, let's see what they do. So at node V2, what do they call V2? V2 is right there. So they got V2 over 50, V2 minus VO, yeah, over 100 equals 0, which they rearranged, and they got VO equals 3V2. Oh, yeah. Okay, so they just did another simple, I don't know, it's simpler than I realized, I guess. So they just did V2 over 50K plus V2 minus VO over 100K. That's that.
So it's almost like the nodal analysis from V2.
So they really did break it into two nodes, even though they're one node. I guess because like even when you have like a super node and you're doing nodal, you still count them as V1 and V2. Even when it's like even in like normal nodal without op amps, you still count things separately. So I guess we should do that. And then I can substitute in 0.9 and just solve for it. So I'm just going to trust that we can solve for VO equals 2.7 volts. And then now that we know VO, we can find I by doing current division. No, that doesn't make sense. Can we do current division? No, just apply Kirchhoff's current law. Yeah, okay, so then we just figure out that...
Well, you know that current is the voltage over resistance, so what you could do is find the voltage at... Yeah. Well, I wasn't thinking that. I was thinking, because we have VO, and you have VO, and then, what's that?
You have the 10K.
You see the 100
right?
kilo ohm?
Yeah.
You could probably find the voltage over that.
That's true, but we don't know. This is not I not there, right? That's something else.
Or what I was thinking was like, what I was thinking is like, since you have VO and then like the 10K, you could do ohms law, but I don't know.
The thing
that seems too simple.
That would be true if this current was I naught, but it's not.
Okay.
That current is I naught, and then it gets split into two different branches there. Right? Yeah, that would be true. If we knew this current, then that would be that.
So I guess you do like KCL, I guess.
Oh yeah, no, sorry. I think now maybe I misunderstood what you meant. Yeah, okay. So to find just this current, and then we could find the other current. We found this one. Okay.
So
yeah,
KCL,
I see. Let's see, how did they do it? Did they do it by KCL, and then they just substitute in the values, and then they just solve. Yeah, so essentially they just say I naught is equal to this current plus this current.
Mm-hmm.
So I naught is equal to that current is VO minus V2 over 100K plus VO over 10K. I know all these numbers. So I naught is equal to V naught was 2.7 minus 0.9 over 100K plus 2.7 over 10K. And I can just trust that we can solve that for whatever number they got. 0.288 milliamps. Okay, so lesson learned from this is even though the two pins have the same voltage, treat them as separate nodes, and just include an equation that says they are equal. That's a good. I guess that's actually the main takeaway from this. That's what solved this whole question. It's just by calling them different nodes and then just including this equation.
Yeah, like what I subconsciously do is when I see 0 amps, I just assume 0 volts, which is wrong.
Well, there's a 0 volt difference between these two.
Yeah, that's what I mean. Yeah,
but
like
not, but not just that. It's not just 0 here and 0.
Yeah.
Here.
I get that.
Okay, great. Thank you for that. Those pictures, Ronak. That's good.
Yeah, no worries.
Yeah, good. 11 we skipped. 13 we did. Okay, 15, and that'll probably be our last question for today. 15.
And I think that's like halfway, right? Because I'm pretty sure there's 14 in total. I don't know.
Yeah, I'm not sure. Yeah.
Does this also include op amps in complex, like AC sort of stuff?
It does not. It does not include that. What's happening?
That's chapter 8, right?
I think so, yeah.
Yeah, that is chapter 8.
Oh, okay, yeah.
Wait, there's AC op amps?
There is AC op amps, yeah.
Wait, isn't that supposed to be like second order circuits? I don't think it's AC op amps.
Yeah, it's not in this chapter. So you see, we have op amps, but they never started talking about AC until chapter 9. So op amps come in. Where does op amps come in? Is it in?
Are we expected to know how to solve them?
My professor did a question with AC.
Yeah.
Yeah, same. You only did one,
it.
but like you didn't emphasize it.
Yeah, I think it's in frequency response. I saw it. I forget where it was.
I think it's chapter 5, right? Op amps.
Well, chapter 5, but where they start talking about AC stuff, because they wouldn't mention it until after chapter 9.
It's chapter 8, no?
Chapter 8 is second order circuits, and so that doesn't start. AC stuff starts chapter 9 here, sinusoids and phasors, right?
I think it might be in like one of the normal AC problems in chapter 9 or something.
Yeah, maybe. Maybe here. Anyways, you can tell this course is gonna be a complicated one. It's gonna be a really complicated course.
Do you guys understand like what's going on in second order?
No.
For a bit,
I guess like a little bit I understand, but mostly because I read the textbook and also mostly because.
Yeah, I didn't read. I probably should have read ahead for like chapter 8, but yeah.
I know it. I always want to read ahead, but like I never have time to read ahead. Just gotta keep up with.
I'm gonna lie, like I understand what's going on, but like I just don't remember the steps, and like I don't know why I'm doing what I'm doing. Unlike first order made more sense though.
Yeah.
Right, let's do this.
Okay, let's try 15. Yeah. So determine the ratio of VO over IS in the op-amp circuit. Okay. Evaluate the ratio for R1 equals that and whatever. Okay. So IS over VO. Interesting. So
could we automatically use that derived equation that we have where it's like VO over VI equals A over 1 plus A sort of thing, and then kind of go from there? Kind of alter it from that?
That would be A over 1 plus A. Well, no, that would just be... That's only for this particular circuit arrangement that we had at the start here. Which is a common one. It's just like a very basic negative feedback loop. But we have a bunch of other resistors in here that need to be part of the function.
Okay.
Right? So, well, okay, it's an ideal op-amp that has a negative feedback loop. So there's 0 amps going in here and 0 amps going in here. That means it's IS going up there, right? IS is going up.
Mm-hmm.
But IS is also equal to, this. So there's the current splits there. IS is equal to that plus that. So I'll call it I2, I1. I know IS is equal to I1 plus I2. And then, which is fine. Then I don't know anything about the current leaving here.
Well, I think you would know. So what the current going into VO would be I2. Could that help?
Yeah, it would be. It would be I2. Yeah. But it's not like it's a resistor, right? It's just the voltage. So VO is essentially just the voltage at that node there. So let's see. Let's just see. I mean, nodal is always useful, so let's just give it a try, I guess. Or should it be K something L? KVL? No. Okay, nodal seems to be fine. So the current leaving, so that's a very simple nodal.
Mhm.
This is just, okay, I'll just call it V1. That's V2.
Wait,
V3.
instead of using that big node as V1, can't you just use V2 all the way? Because like you can just say the current going into V2 is just IS, right?
The current coming in here is IS. Yeah, that's true. I1 is not very necessary here. Yeah. Current going there is IS, and then it splits into I1, I2. In fact, actually, I just realized V1 is equal to 0, and that's because, well, it has the same voltage as this node. That node has a voltage of 0. So, because that's all. This is one node, essentially, here.
Yeah.
So I1 equals 0, which is fine. So then I think all I have to do now is say, well, okay, 0 minus, yeah, I think I can just do nodal there. So yeah, I'll just say V2 minus 0 over R1. First of all, that, well, okay, whatever.
Wait,
Plus,
wouldn't that be redundant because like the current going into V2 is just IS? Or am I wrong here?
yeah, the current going into V2 is IS, yeah.
Wait, so then why are we doing like why are we even using V1 as like a variable in this?
Well, I didn't write it here. I just wrote 0.
Um,
I just wrote 0 there.
no, I just wasn't sure. That's why.
Yeah. It doesn't have to be a variable. This whole node has a voltage of 0, so we just
Mhm.
um,
Okay, so V2 minus V3.
over R3, and then plus V2 minus
Over
0 over R2. Yeah, which is just that. Equals 0. Okay.
And now we just do for V3.
What am I looking for? I'm looking for VO over IS. Interesting. IS is equal to V2 over R2 plus V2 over R3, which is fine. It's fine. I can't do it at R3 though, at V3, because sure I know that. That's V3 minus V2 over R3.
Wait, you know what I just realized? You know how like we said that like the entire left side is just one node from all the way from V2 to IS, right?
Yeah.
Like we can. I just realized like we might need that V1, the initial like smaller node on the left side, because on that like on that node the KCL would be negative IS plus um V0 minus V2 over R1. So like you can just like get a ratio of what V2 is with respect to IS and R1, and then you can just sub that into the V2 KCL.
Oh, okay, so I'd get negative IS because it's coming in, plus
0 minus V2, I believe.
0 minus V2 over R1 equals 0. And then I can solve for, oh yeah, then I can solve for V, yeah, that's good. So IS equals R1 IS equals negative V2. Sorry, going backwards there. I know it's weird going up the page. But that's what we get out of that. And then, is that, yeah, that's fine. That is right. So V2 is that. Okay, so then we can take that equation and go to this. No. Take that equation and go to this. Yes, because V3 equals VO. So take both both this and this, combine it with this equation, we get negative R1 IS over R1 plus negative R1 IS minus VO over R3 plus negative R1 IS over R2 equals 0. And now I can just solve for IS over VO over IS or whatever it is. Yeah. So negative IS minus R1 over R3 IS minus 1 over R3 VO minus R1 over R2 IS equals 0. Whatever, factor everything out. So just take, that's a negative there. Yeah, so move that to the other side, factor IS out. So IS times negative 1 minus R1 over R3 minus R1 over R2 equals 1 over R3 V naught. And we're looking for what? V naught over IS. So it's going to be, factor the negative out of that. So it's just going to be, so negative R3, 1 plus R1 over R3 plus R1 over R2. So this is negative R3 minus R1 minus R1 R3 over R2 equals V naught over IS. There we go. That's what I got. Is that the answer though? So it makes sense that it's in terms of resistors, because then the next one says evaluate for some particular resistor combination.
So, what is this for?
15.
Part A or part A?
A, yeah.
Okay. They got some. Okay. Wait.
It might be
scroll
just in a
down.
different form.
So R3. Yeah, you got it right. They just
Okay,
factored out like the negative, but yeah, you got it right.
Okay, good, great. Okay, so then this
Okay,
is...
yeah, I just want. So are we done? Did we find the solution?
Yeah.
Yeah.
60, and then
Could you just like go over it like one more time?
Yeah,
Yeah.
because someone came into my room and I had to. I was
Okay.
distracted.
Don't
Sorry.
worry. Yeah. Okay, so then I got my answer for B is negative 63.2. Is that right?
They got negative 92.
I might have just done something.
Negative 92K ohms.
Yeah, did they?
Yeah.
Are these all kiloohms? So 20, 25, 40. Negative 40 minus 20 minus 20 times 40 over 25. Negative 60 minus 80 over 25. Yeah, I got negative 63.2. But this is right? This expression's right?
Yeah.
What? 20 kiloohms, 25, 40. 40. 20.
Let me try doing it as well.
20 times 80. 20 times 40 is 800. Negative 92?
Yeah, negative 92.
Okay,
yeah.
This is 800.
100. Oh, okay.
There we go. Okay, yeah, I'll run through it. So what we did is we were looking to make an equation that relates IS and V naught, right? Because we want to find their ratio. So importantly, we did KCL at that node. And so we found that, was it at that node? Yeah, it was at that node. So we found that this equation through doing that. And then we need to find some sort of way to represent V2 and V3. So V3 is equal to V naught. Hopefully that's clear, right? V3 is equal to V0.
Yeah.
V2 is a little bit more complicated. So to find V2, we needed to do nodal with this node. And we discovered that negative IS plus 0 minus V2 over R1 is equal to 0. Rearrange that for V2 here. Whoops.
So how do we get that? So I know because it's leaving the node, it's a negative IS.
Yep. So well no, that's coming in. That's because of that's coming in. That's the negative IS.
Oh yeah.
So from the perspective of the node leaving, it's negative IS, right? Perspective of the node. And asking current leaving, that's negative IS. And then this way is going to be 0. This has a voltage of 0 minus V2 over R1.
And we knew that it was 0 because from that positive terminal.
Yeah, because these are connected. These are the same voltage, and that has a voltage of 0.
All right. Okay, so I understand that equation.
And so then we got an equation for V2, equation for V3, substitute that in, and then just rearrange for the ratio.
Okay.
So V2, oh sorry, V2 is equal to negative R1 over R. Okay.
Negative R1
times
IS.
IS. Okay.
Yep. And rearrange for the ratio, and then substitute in the values they gave us for part B. This is part B. And yeah, there we go. Okay, so I'll check that one off. So we got through a good couple questions today. 1, 2, 3, 4, 5, 6, 7 questions. Well, really 6 because we didn't do 13, or 11. We didn't do 11, but whatever. So yeah, let's finish these sometime this week or the weekend or something like that.
Yeah, that sounds good.
Because it's good to keep up with this stuff.
So I still have that math question. I was wondering if we could just kind of
sure.
Okay, so I'll write it down, or I'll tell you what it is. So it is. Sorry, let me just give me a minute.
Do you know which like chapters it covers this week? Or
in math?
Yeah, for like the quiz.
Oh, for the quiz?
Because I remember like.
Yeah, I don't know.
Okay, so it is y double prime plus a y prime plus by equals negative 9 e raised to the power of 3x.
Yes. Okay, and it says solve this?
Yeah, that's exactly what it says. It says solve.
I got no idea. I've been...
Yeah, okay, so I was asking... Here, you know what? Let me actually send my solution because I didn't get too far.
Yeah, I can get into it, but it gets really complicated really fast.
Okay, so... Okay, so I'm gonna send this. Just tell me if... Okay, just give me a minute.
I don't understand what they mean by solve this. That's a little bit too vague. If you just assume they mean general solution, then you have to split it into 3 cases. If you just assume they mean what the particular solution would be, then I guess I didn't try that, but I think there's some trouble if you do that, and that's probably not what they mean. They would say particular solution if they meant that.
Okay, so I sent this. So this is how far I got, and the person I was talking to said, yeah, like, this is the right process, but the way your C turned out is kind of weird, so it can't be really used to be subbed back into the left side of the equation. You're saying something like that?
Yeah, so you see how you got R1 and R2 there, right?
Yeah.
You have no idea which case that goes into, right? You have no
idea
if that's case 1, case 2, or case
to
3.
make my general solution, exactly. Yeah.
So at this point, you would just have to, if you were to really be, forced to do this, you'd literally have to say case 1, R1 equals R2.
No way, you have to do 3 different cases.
I mean, you'd have to if you want to be exactly accurate, but I highly, highly doubt that's what they meant for us to do.
So I got this in the quiz, and I just was stumped. I literally didn't know what to do.
Yeah,
so
let's see your yp. You did yp by doing c e to the 3x. So y prime p is equal to 3c e to the 3x. Y double prime p is equal to 9c e to the 3x. Something that in 9c e to the 3x plus a 3a a c e to the 3x plus b c e to the 3x equals negative 9 e to the 3x. Yeah, you're fine with how you did it.
Yeah, so then I kind of just factored out a c. And I don't know why I did that, because it's not like there's a c variable on the left side.
Yeah.
I don't know. Honestly, I just didn't know where to go from here. So
Yeah, no, that's fine. That c is equal to negative 9 over 9 plus 3a plus b.
yeah.
Yeah, that's right. That's fine. So your particular, so maybe they meant particular solution because you can't actually solve for it.
Okay.
So maybe they meant particular solution. So e to
Okay.
that would be your particular solution.
Yeah.
Totally fine for that to be, because it's just in terms of a and b.
Okay. What was I gonna say? Okay, so that one question, if you remember that I sent you, it was another math question. It was, let me find it. Right.
Wait, just like a quick question about this.
Yeah.
Where
Yeah.
did the C come from?
Oh, C is just because when you're getting a particular solution, when you're getting just like some particular, you're guessing. Well, it's not really a guess, but you're just using the table method to determine a particular solution. You need a constant in the front, so it's just C, and you need to figure out what that C is in particular. So you need to be able to solve for C.
Wait, but wouldn't that be a problem? Because like when you do the when you get the R1 and R2 like he did, then like you also have to like make a condition where like if like if it's equal to the exponent of the e to the or 3x in the on the right side, then you have to put an x next to the c.
Yeah, but we have no idea anything about the general solution. There's no way, we don't have any way of figuring that out exactly. So
Like, I'm not saying this is wrong, but like for a
yeah,
particular solution, this should be right. But like I just don't know how.
yeah,
Oh.
you're right. But if one of these roots were 3, then you would have a problem. If either
Mhm.
R1 or R2 were equal to 3, then you would have a problem, because then it would be.
So then, like, do you think like if someone gets a question like this, like, do you think they should like or like if we do get a question like this, should we like mention that
Sure,
if that is
if
not
you think of it, yeah, it doesn't hurt to say that. Yeah. But if you don't think of it, it's fine, probably.
So for your particular solution, why would you have to isolate for C to have it equal to your particular solution? So like, for example, you see over here how you have 9C plus 3AC plus BC equals negative 9?
Yeah.
Couldn't that itself be the particular solution?
Well, but the particular solution is this. That is the particular solution. You just have to figure out what C is.
Yes, exactly.
You have to figure out what C is for it to actually mean anything.
Yeah, I had to take a couple steps back.
Right,
I forgot.
Right.
Yeah.
That's the particular solution. This is the whole process of figuring out what C is.
Exactly. Okay.
To here. And then now that's our particular, like our actual final value of our particular.
Okay, yeah. So anyways, I sent the question that I actually asked you about previously. Like it was like a week ago, 2 weeks ago.
Yeah.
Anyway, so I was talking to someone, and apparently what you could do is just simply divide it out. You could just divide every coefficient by 3x plus 9y all squared. And then that cancels everything out, and now you're just left with dx plus dy equals 0. And then you just move everything, or move each thing to the opposite side and integrate. And then you're just left with y equals x, or negative x.
Yeah, you'd have dy by dx equals -1. So y equals negative x plus c. Is that the answer?
I don't know that because it was in my quiz. So
yeah, let's put it in
This
Wolfram.
is like one of
wait,
a
sorry.
text.
So how'd you get to the dy over dx situation?
So divide everything by 3x plus 9y squared. 3x plus 9. You get this part, right? So divide whatever.
Yeah.
So we get dx plus dy equals 0.
Yeah, and then can't you just move the dx over to the
divide by dx.
Why are we dividing? Why it's a plus. So can't you just move that over?
Sure, but we want dy by dx. We want the fraction dy by dx. If we just moved it over, if we just moved it over, it would be dy equals negative.
No, because when it says find the solution, what that means is just find y equals to some function.
Yeah. Oh yeah, so and then integrate that?
Yeah.
Yeah,
right?
that works too. I mean, that's pretty much the exact same thing as what I'm doing. But
Oh, okay.
I was just gonna do it like this: dx, so that equals 0. Divide everything by dx.
Okay.
Right? We get
Oh,
1
and then you
plus
just
dy
bring the 1
equals
over.
dx equals 0. Move the 1 over. Be nice if I could write properly. Dy by dx equals -1. Integrate both sides here. It's a little bit more straightforward. You're literally just integrating a derivative. Right? So you have just y equals -x plus c.
Yeah. Okay. Yeah,
Wait,
it works out the same.
wait, so does that mean, sorry, does that mean like if we get m and n like as the exact same thing, like we can just divide it by the value?
Let's check.
And then
I'm gonna put this into Wolfram and see if that is.
I'm pretty sure this was like a textbook question as well.
Yeah, and I think I had a question like this, and I got an answer like this. So, pretty cool.
My quiz was like completely different. I didn't like get any of the questions.
Yeah.
I mean, I got like the questions. Yes, it's not like that, but they weren't like the same as like they weren't like this. Like,
yeah, and that is the answer. Yep. So it's good.
I see.
worked.
Okay. Thank you very
Okay.
much for the session. Hopefully
Yeah,
we do
no
it more
problem.
often.
Yeah,
And,
yeah, for sure.
All
I
right.
guess
Gotta head out.
technically, just one more thing. Just technically,
Yeah.
by doing this, you're saying that 3x plus 9y does not equal 0. You're saying that because if you by dividing both sides of the fraction of the equation by something, you're making that restriction. So in other words, y does not equal well,
Because 0 divided by 0 is an error.
you can't
right?
divide by 0, right? You just can't divide by 0. So the thing you're dividing by cannot be equal to 0. So essentially you're just saying that y cannot equal -1/3, -1/3. But that's fine because
the
our
extra
solution.
restriction.
Yeah, but that's fine because our solution wasn't even in that form. If our solution somehow ended up being like -cx, then we'd have an issue because we're making a restriction for no reason, really. Then this process would actually be making a little bit of an error because we're saying that y cannot be this. But that's not what we got. We got this. And so our function, our solution, in being in the form -x/3 is not in this form. So it's fine. It's totally fine to do this. Since, we're always allowed to divide both sides of an equation by something. You just have to understand the repercussions of it. So this is the repercussion. And so this is fine. It doesn't change anything. Oops.
Sounds good.
Okay, there we go. That's all my time for today too. So I'm gonna get going. Yeah. But nice to talk to y'all.
Bye.
Are you gonna like upload this?
Yeah.